All right, let's kick off. Good afternoon for anyone here in Europe. Good morning for anyone further west, and good evening anyone further east. My name is Seb Andreas. I'm the CEO here at HAL Robotics. I will be guiding you through most of the presentation and demos today, but I'm also joined by our CTO, Thibaut Schwartz, who will be helping me out with some of the more technical side of the hopefully interesting Q&A that we'll leave plenty of time for at the end of the session. For those of you who don't know us here at HAL Robotics, we're a software company, and we've been developing solutions to make manufacturing robots more flexible and adaptable for past probably nearly 10 years. We specialize in the programming of variable, complex, and unique tasks, from additive manufacturing in concrete, metals, or plastics, to welding one-off components, all the way to throwing and catching cocktails. We initially started off trying to make construction more adaptable and more automatable. But over these last 10 years, we've actually learned an awful lot more about manufacturing, starting with the fact that it's considerably less automated than most people are led to believe, with robots only really being used for the most repetitive tasks. Reality is, however, that very little of manufacturing is truly repeatable. Contract manufacturers and most SMEs are changing the parts they're producing based on client requirements. And even in automotive-like mass production, jobs such as finishing paintwork are still handled manually because the locations of blemishes are different on every single vehicle. Whilst robots can be reprogrammed between runs, financial and time cost of that reprogramming is often prohibitive. More importantly, robots tend not to be deployed because these tasks require tacit knowledge from an expert operator who probably isn't the same person who can reprogram the robot. To both those facts, the labor and skills shortages that seem to be ubiquitous across the industry, and the need for an easy-to-use, adaptable solution becomes increasingly clear. We've taken a kind of three-step approach to simplifying the uptake of robots and automation. Firstly, we think that by combining the strengths of operators and machines, we can create a team that's better than the sum of its parts. That, in turn, allows automation to be used in more places and processes. Collaboration which actually empowers operators to be much more productive and supports manufacturers' growth. And then that reconfigurability leads to flexibility and batches of one being produced with economies of scale. Everything we do is underpinned by our end-to-end robotic middleware, the HAL Robotics Framework. It uses generative robot toolpaths derived from data sources like 3D scans, CAD models, or text in database. And that means that any time incoming data changes, so too does the robot's program. That gets validated almost instantly by the cell's digital twin to ensure any potential errors are caught before runtime. The framework is completely vendor agnostic, supporting robots from ABB, Universal Robots, KUKA, Fanuc, Mitsubishi, and nearly a dozen others. It also exports code in the robot's native language to maintain any integrated safety and system functions. And that's really the basis of our new software, Decode. It's an operator-first software, which can be adapted for just about any process, from finishing to additive to inspection and quality assurance to welding. It's designed to give the operator, the person with the knowledge and experience, enough agency to adapt a process without burdening them with the complexities of robots. For example, in this finishing application, the operator is presented with a straightforward list of instructions and options to run the cell themselves and adapt its performance. They can change the pattern of the finishing pass, its spacing, the robot speed, and a few other essential tacitly known pieces of information. When they hit go, we run a very fast simulation to check for any potential issues and alert the operator that in this instance, the part can't be reached. As soon as the incoming data changes, though, to a part that can be done, the same toolpath generation strategy is applied to the new geometry, the checks are done, pass, and the robot's sent on its way. In the real world, on our testbed here at the office, just a few tweaks to the speed and pattern, and the robot is off. And because few parts are as flat as those cabinets, here we can see an operator identifying regions that need work on a doubly curved part, the operator's skill at identifying defects, collaborating with the robot's precision and tirelessness to execute the job. In this instance, the operator is encircling the region that needs rework with a marker, and a 3D scanner is identifying the part's geometry and that region of interest. Those are then being used as the data input for the rest of the software. In the case of something like a welding application, the operator's options might be a little bit different, choosing work distance and torch angles, rather than the forces and speeds. But the principles remain exactly the same, allowing the process expert and robot to use their skills where they are most needed and valuable, and guiding the operator through their work, whilst of course giving that operator the options they require to adapt the process if any adaptations are needed. So, how do we configure all that for the operator? It's in 4 main stages. We start with the cell's digital twin, adding in the robot, tool, controller, environments, CAD models, signals, and everything else that enables a good simulation of the equipment. We provide catalogs of robots, controllers, and some tools, but also give our users the opportunity to build and model in anything that isn't provided out of the box. With the digital twin in place, we can program the robot, adding in standard instructions like motions, weights, signal changes, or speed through the process by using our parametric toolpath generators, for example, to cover an entire surface in a pattern, as we can see here. We can add variables anywhere we need within that program to allow the operator to make changes before each run and simulate the process to ensure it will work. With the robotics side set up, we move on to describing the process, adding instructions for the operator, triggering external devices, starting the robot, whatever that process needs. It's worth adding probably at this point that the whole software has been designed to be easily extended. So if there are any special steps needed here, they can be added. For example, reading something from an ERP system, writing a log to a database, or even gathering data from some external sensor, as we saw in the polishing demo a moment ago. That's all it takes to get us to our first test of the operator's flow. From here, we can run through, ensure that we're happy with the options and instructions presented, run simulation with any variable changes, and then start sending code to the robot. I'm going to switch over to decode itself, and we can take a look at how it all works. If you have any questions throughout the session, please feel free to drop them in the Q&A box, and we'll go through them at the end. So this is decode. It's already been set up with a session in it, and I think it's probably best to start from the end. This is the operator's workflow, and if we hit run, this is what the operator is expected to interact with as they're using decode. So they receive instructions, for example, in this case, to load the part they want to process into the cell. Okay. And then they can be given options, things we want them to be able to change. All of these are assignable by the integrator. So there's nothing, we don't offer all the options necessarily. These are really a selection of options that we want them to be able to edit. So for example, the step size, we can change down to 10 millimeters, and we can see the pattern that the robot's going to execute. Updating that. We can also ask them to load in a new CAD file. Like this different geometry, ask them which surface we want to deal with. Select top, hit OK, and the toolpath's regenerated based on that input data. We can then obviously rechange our step size if we want to, change the speeds, the hover height, which is just an offset from that. And then when we're happy with our settings, they've already been validated automatically. We check the validation again just to be really safe, because we're not connected to a real robot. We can't upload. We get a warning that the robot's about to start. We accept that warning, and the robot, in this case, simulated robot, goes off and does its thing. If we switch ourselves from simulation to production mode, then all of those instructions that are going to our virtual robot go to the real robot instead. We can see our robot following through our toolpath with the parameters that we've just set up for it. There we go. So if I now backtrack back to see how this has been built up and how it's been set. We said we start with the digital twin, the scene. We have our robot tool attached. Both of these are kind of standard from our catalog. We then have a kind of sequence of references and parts. You can see here we have the main reference, which is our worktop, onto which we have the base plate that the part's been placed, and then the part itself. Each of these with a relative offset between them, so we're not having to work in kind of weird coordinate systems. Everything is relative. And then we, of course, add in the robot controller, which can be configured to match the options and configured to talk to the real controller at the same time. We then have all of our signals. In this case, we have only added a single signal to trigger the tool's activation, which has both a user-readable name and an export override name. So we can use it as being called tool activation, but when it gets to the robot, it's called DO01. Again, trying to keep things as intuitive and legible as we possibly can. Then within the toolpath, there are several things going on. The most interesting of which is probably this polishing pass itself, where we're generating the pattern based on the region that we've selected. There are settings for the pattern. We can make it concentric or parallel lines. We can, again, change some of these settings. This is where we link them to variables for the operator to be able to change them later. We can adapt the targets, ensure that they're always normal to the surface, which is obviously trivial on a planar surface. As you saw in the polishing, the plastic polishing earlier, we can also handle that curvature in 3D. We can apply transformations, so offsets of those targets, automatic rotations of those targets. Configure the motion settings, change what space we're moving in, speeds, the blends. In this case, the blend is linked back to the step size. So the spacing between each of these passes is the same as the blend. Keep the tool pass nice and smooth. And we can change how we jump between different sections of this, what the retraction distance is, what the retraction and approach speeds are, how we move between those spaces, and also what happens along those along that toolpath. So as we approach the beginning of any path, we trigger the tool to turn on. We don't, in this case, do anything at the beginning or end of each path. The tool can stay on throughout the process. And at the end, we turn it off. If we wanted to add things to do, activate the tool just as we contact the material, if we were doing something like a welding application, then this is where we'd add those tool on into the jumps settings that are there. This is also structured to be made out of sub-procedures. So initialize and terminate are sub-procedure calls that we can go and dig into. So initialize, for example, contains the sub-procedure tool off, and then a few motions to move it into the working area above the workpiece, and then the path takes over from there. And if we take a look at what tool off contains, we have a signal action setting the state of the signal to be off in this case, and a wait instruction so that we give ourselves a second for the tool to spin down in the cases, because it's a rotary tool. There's a bit of inertia that we need to wait for before it's truly off. Within then the workflow. And then we can obviously solve and validate the toolpath and dig into the details if we need to through the procedure timeline. If there are any errors, which of course there aren't because this is a demo, we can highlight them within here, and we can also scrub through the timeline if there's anything we need to work out why an error is occurring at this particular location, for example. Or we can reset and run through the procedure as a simulation, skip forwards and backwards in actions, and particularly for things like finishing processes or long-running processes, we can also accelerate time, which is extremely useful. With the procedure then in place, as you mentioned, we can head into the operator's workflow. This is where we set up what the operator is going to have to interact with, essentially. So we can notify the operator, just give them a message that requires no interaction on their part. We can ask them to confirm some sort of information, as we saw loading the part. Ask them to change a value, ask for their input, basically. Give them choices. So which type of part have you just loaded? Part type A, part type B. And within each of those, we get branches. So we can run subroutines, essentially, or sub-workflows based on the choices that that operator has made, based on which part has been made. We might know that we might ask them what material, for example, where the part they've loaded is made of. And in the case of steel, we might need to go slower or apply more force than in the case of an aluminium example. So we can create these forking choices so the operator doesn't need to keep all that knowledge in their heads. We can also change how that works based on pre-designated information and choices that they can make. We then have things like export code. So this is where we generate the code for the robot itself. Groups to keep things nice and organized. Setting the procedure execution, so actually running the robot, simulated or real. Setting variables without the user's input. So like I was saying, in terms of those choices, uploading code to the robot, and validating the toolpath. So once those changes have been made by the operator, we enter this validation step and we'll only upload code to the robot and start its execution if the validation, so we're looking for kinematic errors, looking for singularities, looking for out of reach exceptions, things like that. We'll only upload the code if we pass that validation step. And so there's a level of safety inherent within that. We also have these two elements here. So the first or the second, but the more interesting one is our variables, where we can have a look at what our values are currently, change those here if we need to, and they'll be propagated throughout the rest of the software. You'll note these are all set to manual. If we have time, I'll hand over to Thibault to dig into some of the non-manual options that we have for setting variables as well. And then we have an asset manager. So anytime these elements have been imported, there is conversion going on between step files, in this case, and our internal data formats. And those are all cached so that if we go through and load a new part, the same part that we've loaded previously again, we don't have to wait for that long process. Obviously, with something as simple as these plates, it's not too bad. But when we're dealing with 2/3 of an aeroplane fuselage or a locomotive bogie, those things take a bit longer to import and process. That's decode. I can't see any questions at the moment. So I will hand over to Thibault to go into some real nerdy goodness with our SDK sitting behind the scenes. Thibault.
All right, can you hear me? Oh, good. So I will just add a few things to what Seth has just showed you about starting this time from a completely blank document. So I just started a new project, and there are a few things here that you can see is that the different parts of the software are always asking you if something is incomplete or if you have an error locally or anything. So you are always guided through the definition of your project, and you don't have to like look forever where there might be an issue. You know where to navigate immediately. and fix that. Another thing which is quite interesting is these little links here making variables. So here, for example, I have my y reference coordinate bound to a new variable. These variables can be manipulated manually, but they can also be linked both as inputs and outputs to Grasshopper. So decode runs on top of Rhino, which means that we are compatible with 50 plus CAD extensions, CAD file extensions, so we can import pretty much anything on the market. And it also means that we have access to all Rhino plugins and all Grasshopper plugins that you have installed on your machine. If you open Grasshopper from decode, you have access to everything you've installed. And it is possible to drive decode from Grasshopper. So here, for example, I have my reference linked to my y coordinate variable. And maybe what I want to do is to specify this coordinate in Grasshopper. So what I can do is place a new length unit parameter from HAL directly in Grasshopper and select my Grasshopper parameter. Now, if I change value in Grasshopper, then I will be changing my reference in decode. So that's the basic principle. And then we can go much beyond this very basic logic. Can I also export back existing values from decode to Grasshopper? So here, let's say I want to export this variable again back into Grasshopper. Now, as you can see, I am importing Grasshopper value into decode from Grasshopper, and then I'm exporting transform decode value back into Grasshopper. So you can have an exchange of data between things that you program in Grasshopper, or if you are an existing HAL SDK user, you might already have definitions, custom tools, toolpath strategies that you already developed over the years. You can use decode and your existing files, or use Grasshopper to extend the features of decode pretty much anywhere in the software. Because now, if I come back in the scene, for example, and I want to add a new robot, what I can also do is say, I don't have a robot. I just want to get a robot from a variable. And then if I simply say, this is a robot from Grasshopper, I can go back to Grasshopper and select a robot, or use an existing robot I already have. And like that, I can just pick my robot in Grasshopper, and it is now in decode, and I can attach a tool or use it in decode. So the integration between Grasshopper, Rhino, and decode is absolutely seamless. You benefit immediately from using decode from hundreds, if not thousands, of plugins and existing code files available from the Mechanic community. I'll give the mic back to Seth now.
Cool. Thank you, Thibault. So for those of you unaware a little bit of the history of our software, we have had Grasshopper as a visual scripting platform built into McNeil's Rhino 3D, which is very useful for generating geometry and doing kind of parametric modeling and generative design work. And we have long had an SDK that's built into Grasshopper as a means of parametrically programming robots from that visual scripting interface. And so for any existing users who want to use their existing Grasshopper knowledge to extend the functionality of decode, if there are features that aren't there, then that's absolutely possible. And you can use decode as a means to simplify the user interface. I can see there's a hand up. I don't think mics are active, so if you can post a question in the Q&A instead, then we can answer that. Yeah, so Rush, I can see that your hand is up, but I can't enable your mic. So if you can post something in the Q&A instead, we can answer that for you. And obviously, if there are any other questions, please feel free to pop those in the Q&A box, and we can go through those now. Cool. So we have a first question through from Justin. That says, in the doubly curved polishing example, it seemed there was a vision system integration. How does that work in decode? So it's a very good question. If I still have my screen up here. So there is vision integration in that particular case. And the way that works is essentially by extending these workflow steps. So the extension isn't installed on this PC currently, but as well as having here, for example, upload code or set procedure execution that talks to a robot's controller. By adding the vision extension, we can also say request 3D scan from, in this case, we were using a MechMind device. So request scan from the MechMind device, it will ask you in the configuration to set the IP address, the resolution, the shutter speed, the number of passes, things like that, that we need to be able to parameterize that configuration. And so within this workflow step, we can communicate to the other devices that are associated with the scene. And then, as Tibor has shown already, there's the variables can be set from external sources. So in this case, he was showing you the Grasshopper parameters, but those sources can also be a file. In the case of a point cloud, for example, if we're saving stuff to a point cloud to a file or receiving a point cloud back in, we can assign those values back to a variable, which, as we saw in this case, then get processed again all the way through the chain, and we generate toolpath based on that. The way that works in practice means that things are extremely flexible. So we are a robotic software company. We're not a vision company or a vision software company. We know there are people who do that better than we do out there. And so what we can do is actually call out from within decode, call out to their software to do some of that vision processing for us and get just the regions, for example, back. So in the case of that doubly curved polishing example, we built that bit of vision software ourselves. But if there was a GOM system that was looking for deviations between nominal CAD parts and scan data, only had to go and polish the bits that were outside of tolerance, then we could get that data back from the GOM system and say this region and this region are out of tolerance, and use those as the input regions for the polishing. So it's super flexible, and it comes in those extensions to the software. Is the long answer to that. I hope that answered your question. Can decode integrate with, can decode integrate with 2 robotic arms with different tools and a positioner in the same file and same workflow? So the HAL Robotics Framework can handle multi-robot and positioners. These aren't things that we have in decode at the moment. We're really hoping decode stays as the kind of simple, easier to use side of things. Long term, it's definitely something we intend to have. If, however, for the time being, you have a multi-robot system, particularly if it's something that you're programming in a more traditional way at the moment, we would think that you probably have the requisite skills to get involved with the Grasshopper SDK that we provide. There's a slightly higher barrier to entry, but it has all that functionality in it. And there are ways to use decode if you need to give people simplicity to change a couple of parameters in there. As Thibault's just shown, we can actually use decode as a front end to hide a much more complex Grasshopper SDK scene in the back. I don't know if there's anything you want to add to that, Thibault.
I just wanted to add a bit more concerning the extensions for sensors. So the entire software is modular, which means that the main screens you see, the content of every screen, like the types of objects you can build, the way you build them, sort of settings you can specify here and there, and also all the geometric processing, everything can be extended from modules that you install when you install decode. So for example, right now, if you use our installer, you will have access to a lot of modules for different robot brands. And we use exactly this same system to deliver brand-specific compatibility for sensors and hardware, and also to add functionalities for specific customers. So if you have very specific requirements for a process or for a cell that you would like to add to the software, we can also customize the content of decode for your applications.
Thanks. Next question I've got here says, when will decode be available publicly? So there is a beta available publicly that you can access now. If you go on to docs.hal-robotics.com, you'll see a get started guides to be able to go through that and get set up. There are currently a few limitations. The biggest of which is that we have temporarily deactivated the save functionality because there were a lot of changes happening. That will be restored and available next week. Almost certainly before the beginning of next week, it will get pushed out over the weekend, so that it's ready for people next week. So yeah, if you're ready to start trying it out, then it is there waiting for you, ready to be used. And next week, hopefully, there'll be a few. You'll be able to save things as well. Another question about the doubly curved example. We said we were looking at just the circled regions through decode. The bits that are polished, what is the origin of the output path to the robot? Is it the Cartesian provided from the MechMy device and streamed to the robot, or are the shaded regions then just contrasted with the CAD model, put to the CAD CAM environment and executed? I hope it makes sense, and I hope my answer makes sense. So in that particular scenario, we have no prior knowledge of the part itself at all. So we are inferring both so we're taking the point cloud data of the part. We're extracting the point cloud data of the regions. We're reconstructing a bit of geometry based on that point cloud data and generating a path on those regions exactly as we are in the demo that's still on screen at the moment. But that's not the only way to do things. So if we had those regions identified within within another piece of software, and we were just given some areas back, we could project those back onto the geometry of the normal CAD data and use that to get the normals and things like that from the normal CAD data. And the same is true if we had, if we were looking for seams within multiple parts that we needed to weld, for example, and something could send us a line back, we can look at the normal CAD data and say, all right, well, we're trying to track this line, and the normals of the two surfaces that was clearly supposed to be joining is this way, and therefore we'll try and track along that seam. So the kind of non-committal answer is we can do whatever we want with the data that's coming in. That Grasshopper SDK side of things that Tibor showed off a little while ago is extremely flexible, and the extensibility that he spoke to even more recently makes the software very, very flexible in that regard. So there are almost infinite ways to interpret the problem, and it's really about, or at least we really see it as giving you the tools to be able to deliver the process in the right way for you. So yeah, we're not saying this is how anything should be done in particular. We're really about giving a full tool set out so that you can make the process work in the way that you need it to work. We know that there is so much variability, even amongst the same processes being done. They're done in uniquely different ways based on how the parts have been treated beforehand, what the geometry of the parts are, exactly what the robot system is, how the robot's set up, what the tool is, and so there is no one size fits all solution. We know that, and so like I said, we're aiming to give a toolbox and a flexible toolbox. I hope that made sense. So, I don't see any other questions. I don't see any in the next minute or so. Then I will wrap this up and give everyone 20 minutes of their day back. Excellent. Glad, Scott. Cool. Give you till 22 to finish typing any questions if you are furiously typing anything at the moment. Please raise a hand if you're typing something, just so that we don't cut you off. You can always get in touch with us through our contact details, which are on screen at the moment if something occurs to you at a later date. And if you do pick up decode and give it a shot, please let us know if you have any feedback. It would be, yeah, we're both positive and negative. It's a new product and we're keen to improve it and make sure it works for the audience that it's intended for. One final question: the recording will be available? Yes, it will be sent out automatically by Microsoft Teams, hopefully. And we have people who are registered as attendees who will tell us if it doesn't go out, probably in the next day or two. Any final thoughts from you, Tibor?
No, I think that we spent a little bit of everything. We would be curious to understand what you would like to achieve with this platform if you had access to it. For example, what sort of application or process you're aiming for, because there's always a possibility for us to make your life easier by prepackaging geometry tools or any other nice UI to make your life easier. So as it is our priority now to really deliver the easiest to use and at the same time most flexible, more flexible tool to use to anyone, please send us please feel free to send us suggestions about tools that you would like to see in this package, and we'll see if we can add it.
So thank you all for joining us. And as we said, please get in touch if you have any feedback or any suggestions for us. Thank you very much. Bye-bye.